Hi everyone. So we are glad to have Yichen Xu, who's a postdoc at Cornell, and he's going to tell us today about fault-tolerant protocols through space-time concatenation. So Yichen, go ahead.
Okay, yeah. Thanks, Arpit, for the warm introduction. And yeah, it's a pleasure to, I guess, be online at Virginia Tech and talk about my recent work on fault-tolerant protocols through space-time concatenation. And this is actually a joint work done by me and Arpit, and the paper is going to come out soon. And that's partly the reason why I'm talking about this here. Okay, so let's jump in. So, I guess everybody here knows a little bit about some names or some ways that people achieve fault tolerance. Conventionally people have been talking about static stabilizer code, and nowadays with the development of the novel protocols of quantum error correction, people understand that there exists a novel type of fault tolerant protocols, which is usually referred to as dynamical codes. So these codes, instead of having this one static stabilizer group, the stabilizer group of this dynamical code actually evolves over time. So here I'm showing that the stabilizer groups can evolve from ISG0 to ISG1 to ISG2, etc. And it's often periodic. So after several rounds of this evolution, you will get back to the initial stabilizer code you started with. And so we adopt the notion of dynamical code to describe, this one period of dynamics. The notion of dynamical code really, incorporates, other existing fault-tolerant protocols, for example, subsystem code. So subsystem code can also be implemented in a circuit with, time varying, ISGs. But the logical space is static, so it doesn't evolve over time. It doesn't evolve when the circuit is evolving. And it also incorporates, our conventional understanding of static stabilizer code, which is just I give you a stabilizer group, and hence the logical space. So everything is static over there. All right. So I'll give you one kind of interesting, non-trivial example of dynamical codes that people have been talking about a lot, which is the Hastings-Ha Fouquet code. So this code can be realized either on a honeycomb lattice or on this square octagon lattice. So I'm choosing this because we're going to talk about this again in our work. So on this square octagon lattice, the qubits are living on vertices. So and the code is generated by a periodic measurement schedule. So in the round zero, you measure the green checks, which means on every green bonds there are two qubits. So you pairwise measure their poly z's, so the product of their z's. And at round one, you measure the product of poly x on the blue bonds. And the second round, you measure the product of y operators on every red bond. It's a typo. And you repeat this protocol over time. And at each round, after you complete each round of measurement, the ISG is a toric code, but the logical information will evolve over time, and it's been dynamically generated by all your measurement protocols. And since then, it's been a while, right? It's been a few years now since Hastings and Ha proposed their protocol, and we've seen a lot of recent developments of other examples where ISGs are different. Sorry, is there a question? No. Okay. So we've seen, other examples coming from, different groups, which includes, a CSS version of the Hastings-Ha code, which only involves X and Z pairwise measurements. And we also have, the 2D Fouquet color code, whose ISG is color code instead of toric code. And we also have these fractonic Fouquet codes in 3 spatial dimensions, whose ISGs are, either X cube or checkerboard. So these are fractonic codes with extensive logical qubits. Okay, so now it comes to the problem of whether you can generalize these constructions to any kind of good static codes you want, right? Because there has been intensive studies of good static codes. I'm talking about, for example, this quantum LDPC, the different classes of LDPC codes, which encodes extensive logical qubits with low overhead. So this is a natural question to generate all these, Fouquet protocols and construct, dynamical LDPC codes, maybe potentially with, a restriction of spatial connection. So we want to be, flexible in our construction. So before we dive into our construction, we need to talk a little bit about the toolbox that we're using, which is ZX calculus. So we're going to write our circuit that implements the dynamical codes using the notion of ZX calculus. So this is kind of a torn down version of tensor network. So if you're familiar with tensor network, in ZX calculus, there are really just two types of tensors. This what we call an X spider and what we call Z spider. So the X spider is this white circle with some phases in there. And so mathematically, this is equal to a giant projection onto everybody's pointing x equal to 1, plus everybody's pointing x equal to -1 with a phase alpha. And similarly, for the z spider, it's mathematically equal to a giant projection onto z equal to 1 or z equal to -1 with a phase. So the convention, goes with any number of legs, but it's special when you have one leg. So if you only have one leg of these spider, we call it node. So it's a single leg node, and a single leg node describes, initialization of a qubit, or just projectively measure it in the spaces, and you get this outcome. So a single leg x node is, x plus e to the I alpha x equal to -1. So if alpha is 0, we don't usually write the phase. We just write the white node. So the white, x node without any phase is actually plus minus, which is actually a basis of 0. So that's a little bit tricky, like when you navigate in ZX calculus, like the x node with a single leg is actually initialization in z equal to 1 basis. Yeah. And any nodes with two legs are unitary gates. So for example, the familiar Hadamard gate is represented by this box. So mathematically, it's this matrix that we all know. And in terms of VX calculus, if you want to express Hadamard using all these spiders, what you have is, you have 3 pi/2 phases and a overall phase, and you can think of it as some orbital rotations. And entangling gates in VX calculus are expressed, as two connected nodes. So for example, the C0 gate can be represented by this diagram. And this should really be interpreted as, the time is going in the horizontal direction and the gates are acting in the vertical direction. And there's an X node and a Z node. So the convention is that the X node controls the Z node is a controlling qubit, and the X node corresponds to the target qubit. And for CZ, it's basically two connected Z nodes with a Hadamard gating site. Okay, so after these notions have been introduced, we also introduce, rewrite rules of ZX calculus. That's the reason why, ZX calculus is so flexible in describing quantum circuits. So the most important rewrite rule of ZX calculus is the spider fusion rule. So imagine if you have a bunch of spiders in one color, it's either X or Z. You can just basically fuse them. It doesn't matter how many legs there are connected in between. You can just fuse them directly, and their phasors will be added. This actually can be easily seen from the expression, because this is basically a giant GHZ state, right? Everybody's polarizing in the same direction, right? So if you connect all these legs, they're just going to be just going to be trivially fused. And similarly for Z node. And this is a rule of spider fusion. The second rule is color change. So basically, if you have a node and you conjugate, every leg by the Hadamard, it changes the color from X to Z or Z to X. The third rule is the Hopf rule. So the name Hopf comes from Hopf algebra. But pictorially, what happens is, if you have a pair of X and Z nodes with two legs connected between them, it looks as if they are not connected. So this actually can be derived from axioms of ZX calculus. The fourth rule is bialgebra rule. So it works for a pair of faceless nodes. Remember, if the face is 0, we just don't write it in the node. So the bialgebra rule means, you can actually sort of commute X and Z nodes through each other, but you pay the price of generating more nodes. And finally, the extra rule that I'm quoting, that the pi node propagation rule will be important to understand understand the error and fault tolerance of ZX calculus. So
Using the color change rule, it's easy to see in the diagram that you wrote for CZ on the previous slide, right?
yeah.
Because I'm just saying for the audience, like if you take this Hadamard and pull it up onto the horizontal edges, then it's obvious that from the C naught representation, we can get the CZ representation.
Yeah. Yeah, so the color change rule is really like if there's one Hadamard gate here, if I only have one Hadamard gate here, on the right-hand side, I will have all the Hadamard except for the leg that you used to have Hadamard gate. So I can pretty much just push the Hadamard gate from one leg to all the other legs. And similarly, that this pi node propagation rule is I can push, this pi node of Z from one leg to all the other legs. And this also follows from the reason that, it's a giant GHZ state. So it's stabilized by all for example, this X spider is stabilized by all the Z's with a phase, right? So so that's why, if you literally act these bunch of Z's, right? Every pi node, every -1 phase is just simply a Z unitary, right? If you act all these Z unitaries on this ket, what you'll get is the phase will be flipped because plus goes to minus. All right. So the final bit of information that we need from ZX calculus is how to track the flow of Pauli operators in this tensor network in the circuit. So X operators will be denoted by red lines, and Z operators will be denoted by using green lines. So what this means is, for example, if you focus on this X node, since X node is stabilized by any pair of X operator acting on two legs, remember it's a GHZ state, so that means X it can be stabilized by any pair of X on the diagram, right? So whenever you have a flow of Pauli operators that hits the X node with an X operator, it can go out from the node on another leg in X. But since the X node is stabilized by all the Z's, the Pauli web of Z, if it hits the X node, it just goes out on every leg of the X node, and vice versa for the Z nodes. And when you have Hadamard gate, it just simply means it changes the color of this Pauli web. So let's do an exercise and convince ourselves that that the ZX diagram on the right is a measurement of the product for Z operators. So to do this, I might need to annotate. Yeah, so let's see, right? So we have Z, 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 Z coming on the incoming legs, right? So they're marked by this green shaded legs. So after going through the Z node, right? Because we have a Z operator hitting the Z node, it can go out on any of the two outgoing legs. So let's suppose it goes here, right? And let's check. Okay, yeah, it looks consistent, right? So because if you focus on the X node is stabilized by all these all the Z's coming from all these legs. So this means that this circuit actually maps ZZZZ to 1. Right? This circuit maps the ZZZZ to 1. However, you can also say, okay, what in practice is this ZX diagram is actually talking about, right? So remember, using the spider fusion rules, I can break down this X node in the center, right? I can break down this node to a series of X nodes because they fuse to a single X node. If I break them up, and you can clearly see what happens in the circuit, right? So the circuit actually consists of 4 C0 gates, right? Initialization in Z basis and a projector measurement in Z basis. So the difference between the left ZX diagram and the right ZX diagram is that the right is of operational meaning. It's what we call a circuit layout. So in the circuit layout, you have to specify, the measurement outcomes of this qubit. So remember on the right, we can clearly see that there is another ancilla introduced inside to addition to these 4 qubits, and the plus and minus one is the measurement outcome of this ancillary qubit. So the two ZX diagrams are not exactly equivalent to each other, but if you want to convert an abstract ZX diagram to a circuit diagram, you have to you just have to do it. You have to record the measurement outcomes. And if you don't write plus or minus one, just simply write an empty node without any phase, it just means that you post-select your measurement outcome to be 1 instead of recording it in a notebook. All right.
So the two diagrams are equivalent if you have plus 1.
Yeah.
In the node.
Yeah. Okay. Yeah. If you have any questions, just stop me. Okay. Yeah. Because this is going to be very, very like general, and yeah. All right. So let's move on. All right, so let's go back to constructing dynamical codes. So we give our own definition of dynamical codes, which is very practically oriented. So what we say is that you have this time going in vertical direction, right? You have some incoming legs that represents a static code, which you can mark it as NKD. N is number of physical qubits in the static code S. And K is the number of logicals, and D is a code distance of the static code. And the dynamical code is essentially, a measurement protocol that, that measures every stabilizer in this stabilizer group. But in addition to that, it needs to generate a new stabilizer code when the dynamical code is finished, right? So the second condition here is that, on the outgoing legs, it should support a dynamically generated code, S bar, and S bar is also an NKD code, but we don't have to assume that S is equal to S bar, but for convenience of a lot of our constructions, we usually assume that S and S bar are the same stabilizer code. And the third condition is obviously, this code needs to have non-trivial logical space, which means that whatever logical operators you have for this incoming stabilizer code S, it has to be mapped to a logical operator on the outgoing legs. So that's the 3 conditions that we define a dynamical code. And just a very important notice. So this diagram is a little bit different from an actual circuit diagram, because all these legs that pointing downwards and upwards, all these legs represents not the physical qubits in the dynamical code. They represent the physical qubits of a incoming or outgoing stabilizer code. So the number of legs pointing downwards is equal to n. It's not the final number of physical qubits inside the circuit. The reason will be explained very shortly. So our strategy of constructing, this dynamical code is what we call a gadget decomposition. So we break down our dynamical codes into, small blocks in spacetime, and these blocks are connected to each other, and these connections can be, viewed as a temporal dynamics. So in this way, we can, materialize all these constraints that we put on dynamical codes to the level of this local gadget. And we know that, this idea wasn't really something new. And I think we have an expert in the audience that, wrote these 2 amazing papers that talk about, building quantum codes using the so-called quantum Lego. And, if you're familiar with the quantum Lego story, this is basically a dynamical generalization of the Legos, where, every piece of your Lego is not only a static, is not a static stabilizer code, it encodes some dynamics. With some temporal order. And furthermore, we can, based on the incoming and outgoing stabilizer code that we want to generate, we can design these Legos ourselves. And oftentimes, they will actually correspond to some code that we're familiar with.
Sorry, I have a question.
Yeah.
So do you still define it as a dynamical code if the stabilizer measurements are the same at every time step? Or does it have to be Like, or is it only dynamical if like you're making some change to the stabilizers?
Yeah, so like if there's no change in stabilizer, then that's still an example of dynamical code. It's just like there's no evolution of stabilizer group.
Yeah, yeah.
It's the I mean you can call
That
it
would be the
a
standard setting, right? In a way,
yeah,
or no?
that's usually what
Okay.
people do, like in the
Yeah.
standard set. Yeah, exactly. Yeah.
Yeah, so this is a more general picture for which that case is a special case.
Yeah.
Like
Yeah,
this.
that makes sense. And like in the previous slide, you had this kind of diagram with like incoming stabilizers and outgoing ones.
Yeah.
Like, is it part of this to figure out like how to from the how do you figure out this sort of what S bar should be like this new stabilizer set?
You can just so in our constructions, most of our constructions, we just assume that S bar is S for sake of convenience, because if S is equal to S bar, you can repeat this block, right? Remember, if S is equal to S bar, like here, it means that ISG0 is equal to ISG4. So you can directly repeat all these like 4 layers of dynamics over time, right? But if S is not equal to S bar, then there's some subtleties that you cannot just simply say, because it measures the thing that the dynamical code measures and the thing that dynamical code generates actually doesn't agree with each other if S is not equal to S bar. So it creates some practical trouble of reorganizing your measurement schedule so that S bar is evolved back to S. So when we are trying to construct dynamical codes ourselves, we usually assume that S is equal to S bar.
Oh, I see. But I think there was a recent paper of like Gottesman and others where they somehow had a way to figure out what S bar would be, or they had some way to change the stabilizers, right? Um, I don't know
Uh,
if what they did is related to this work that you're presenting.
you mean that they are doing a dynamical code switch or what?
I think so.
Okay.
So we can look for solutions for given S and S bar.
Yeah.
Uh, but it's just that if you so you may not find a solution if you choose a certain S bar, for example, but you can look for solutions. And let's say you find a solution, but then you want to repeat this dynamical code to get a fault tolerant protocol. For that repetition, you might want to go back from S bar to S. And so you will get a block that is sort of periodic, and then you can keep repeating it. So you go from S to S bar, you find some solution, and then you rewind from S bar to S, which Yichen is calling a subtlety. And then you can repeat that block because now you have a periodic block which sort of can be repeated over time.
I see.
Yeah, thanks for clarification.
But if you still assume that S bar is equal to S at every time step, then this is um then it's the standard setting, right?
Yeah, in the standard setting, S is always equal to S bar, and and always equal to the stabilizer group that you're interested, like static stabilizer group that you're interested.
Oh, I think
Then what is dynamical about it then?
there's
I think maybe it's just a semantical thing.
no, there are instantaneous states within the gadget, as you can see, and S and S bar are the incoming and the outgoing stabilizer groups. So it's not like, so you have instantaneous stabilizer groups that are different, I mean, that are evolving.
Yeah. So I mean, going from this picture to this picture, S and S bar will be ISG0 and ISG4,
Sorry, what is ISG? I think maybe I missed.
instant stabilizer group. So the
Oh, okay.
stabilizer group at this moment. Like you
Okay,
can
those can
do
be different.
some dynamics in the purple layer, and then the stabilizer group might change. And you do this for green layer, things might change. But eventually, if you complete the entire dynamical code, it's like you complete this entire box here. If you complete this entire box, you will stop at some stabilizer code, which is ISG4 in this case. So ISG0 and ISG4 are literally S and S bar in the previous slide.
Oh, but and those are you assume to be the same. It's somehow imposing that kind of boundary condition or something like this?
Yeah, it's kind of boundary condition. Like if you impose it, then you can just directly evolve these 4 layers. Like you can repeat these 4 layers over time. Yeah, but if ISG4 is not
Oh, okay.
ISG0, then you have to actually flip the order.
Oh,
Right.
now I understand. Okay, because you want to concatenate the scheme onto itself, so then it makes sense to actually have
It's not
binomials together.
concatenated on itself. It's like repeated over
Or
time.
repeat. Okay,
Yeah,
sure.
it's
Yeah, okay,
repeated
yeah,
over
yeah.
time. Yeah.
Yeah, yeah,
Yeah.
yeah. Okay, this makes sense. And actually, maybe I can just quickly put this paper that I was referring to.
Sure.
We I'll just put it in the chat. It's only because I'm curious to know how it relates to this work, but because I'm also somewhat new to this whole area a little bit. So
I see. Yeah. I'll check the paper out. Yeah, thanks for sharing.
So I have a question.
Okay.
So does it mean also that L and L bar are also same?
Oh, very good question. So wait. Very good question. So L is a logical operator, right? And L bar is
Yeah.
another logical operator. They don't have to be they don't have to be the same.
Okay.
The entire point is that the entire logical space will be isomorphic to each other. So this curly L will be isomorphic to curly L bar, but this exact logical operator L might not be mapped to the exact logical operator L bar. For example, if let's say you have an incoming toric code and you have an X logical, right? And we will show that, for example, actually Hastings and Ha already showed that, the incoming X logical actually will be mapped to the outgoing Z logical. But the point is that the entire logical space is preserved.
Okay. Thanks.
Yeah. Yeah, so if you project this dynamical code into the logical subspace, it acts as a unitary. Right? If you project out all these S, you just working this S equal to one subspace, then it's a unitary. But this unitary doesn't have true identity.
Good.
All right.
Sorry, I have another question.
Okay.
So if we go back to the original, the one where you had the gadgets, yeah. So how do you choose these local spacetime gadgets? Maybe it's the next slide. Yeah, how do you choose
this is what I'm going to talk about.
Oh, okay. Yeah, maybe I'll just okay.
Yeah, exactly. So now I'm talking about how you're going to fix like what you're going to put, right? What are pieces of your Legos, right? So I'm trying to fix all these gadgets on this diagram by enforcing these conditions, right? So I'm trying to find a way to enforce every incoming stabilizer is measured, outgoing stabilizer is generated, and logical is preserved. So, for example, if you have an incoming stabilizer S that's supported on these four sites in the static code setting, you want it to enter your dynamical code and it just gets mapped to some connections between the gadgets and they never go out, right? If they never go out, then you're good because S is measured by the circuit. And similarly, if you have a stabilizer in your outgoing stabilizer group, you want it to be generated, so you only want it support on the outgoing legs and the what we call the internal legs. So the job of us is now to determine that how this stabilizer is mapped to these bonds, right? So you will see that this incoming stabilizer is mapped to all these bonds, and these bond operators are part of this what we call the poly web, right, on the ZX calculus. So it's important to figure out what are the bond operators. So once you figure out what the bond operators are, you're essentially fixing the gadgets. Since the gadget will map the incoming or outgoing poly operators, which are part of the stabilizer, to the bond operators. So the gadget functions as a local encoder, right? Functions as a local encoder that maps incoming outgoing poly operators to bond operators. So we need to find a way, to consistently assign, bond operators, because you will have incoming X, incoming Z, and the bond operators has to, reproduce their algebra, right? So that things can be consistently coded. So there are, various constraints that we have to satisfy. So by solving these constraints, we will eventually determine, what kind of gadget that is. So what kind of encoding map that gadget needs to produce. And based on the encoding map, we can figure out what's inside the gadget.
Sorry, so you choose S bar first, or you choose the final boundary condition and then you try to solve the constraint satisfaction and then you figure out what the gadgets are?
Yeah.
So I have a question about, like, suppose I know the instantaneous stabilizer group and then I know that their corresponding code all has some distance guarantee, right?
Yeah.
But then does that necessarily mean that as a whole in the space-time dynamical code, that the whole thing has a distance guarantee or is not sufficient for that?
Awesome question. So so there is a theorem that we recently proved, which is so we know that of course, like there's a space, like there's a that's code distance just for S and S bar, right? And there's space-time distance inside your circuit. So if you're, yeah, so yeah, the theorem's here. So if the mappings onto these bond operators preserve what we call the geometric locality requirement, which means that, you know, these bond operators only stays between these gadgets that are involved in the static stabilizer, then your code distance is preserved. So there will be no, like the constraint means that there's no bond operator that leaks to nearby gadgets. Like if you leak, you're actually paying the price of, you know, decreasing your space-time distance during this dynamics. But if your stabilizer, incoming or outgoing stabilizer, only stays connected between these gadgets, then, you know, essentially what you have is, you know, when you repeat this dynamical code, these polywebs will be confined in the geometrical region of the dynamical code. So the space-time detector, which detects, you know, any errors that happens during the circuit, these space-time detectors are all local. So in order to fault all these space-time, in order to not fault the space-time detector, but to fault the logical directly, you have to, you know, basically having a polyweb that looks like very similar to the logical error that faults the stabilizer code. Yeah, so if you respect this geometric locality, then we can guarantee that, you know, it has a code distance that will be inherited from the code distance of stabilizer code.
Thanks.
Yeah. All right. So now suppose you figure out what the gadget, what inside the gadget is, right? It's essentially a ZX diagram, like every circuit can become a ZX diagram. So your next job is to, you know, really materialize it into a circuit, because as we mentioned, you know, these incoming and outgoing legs, they're not physical. They're part of this, they're part of the static stabilizer code that we know that exists, you know, between the dynamics. So this might look a little bit confusing. So we flip time from left to right. We just focus on one gadget. We focus on one gadget, and it might have some incoming legs and outgoing legs. Time is moving from left to right, and it has these internal legs. So the internal legs is pointing up and down. All right, so this is what we have if you just, you know, rotate that space-time circuit diagram by 90 degrees on one gadget. So once you spell out what's inside this gadget MI, it's a ZX diagram, but this, you can always bring this ZX diagram in this form. So it might be some really, really complicated stuff inside the box, but you can organize it in 3 stages. So the first stage is these legs, these incoming legs will be mapped to more legs. So these more legs are actually the physical qubits that are part of the dynamical code. And then these physical qubits undergo some inter-gadget dynamics, which is represented by ZX diagram. You can have all sorts of, you know, different dynamics based on, you know, our algorithm that determines the gadget itself. And finally, the diagram goes through the third stage, where all these physical qubits merge into, you know, the outgoing legs, which, you know, host the static stabilizer code that you want. Yeah. So we won't see these legs in the actual dynamical code, because on the diagram we can actually merge this dual spatial encoder with a spatial encoder. So it becomes a circuit that only knows that you have this many physical qubits incoming and these many physical qubits outgoing, right? And they're literally the same. So the third row is a circuit implementation that of the dynamical code that we designed. So it's a little bit confusing that, you know, in the first row, that's what I'm always showing you in the beginning, that, you know, you have some incoming outgoing legs, but these only supports static stabilizer code, and the actual dynamical code happens in the third row, like in the circuit layout, where the number of qubits doesn't change. Right, you can call some of them physical qubits, some of them ancilas, but all of them are physical qubits, which are part of a circuit that evolves over time. Yeah, so this might look a little bit abstract. So let's just jump into an example, which is the Tor code. So as I said, in order to perform in order to construct a dynamical code on top of Tori code, what we do is, we kind of replace all these data qubits in the Tori code by the gadget that we want. So the gadget now is laid out in the 2D square lattice, and the incoming leg and outgoing legs in this figure is pointing, bottom left and top right. And so what we want is, the dynamical Tori code measures all these four-body stabilizers in the incoming Tori code, and it generates stabilizers of the outgoing Tori code whilst preserving the logical information, right? So, for example, in order for the incoming four-body X operator to be measured, the X stabilizer is supported on the shaded squares, by the way. So they have to be mapped to these four bonds. So these four bond operators, so we parameterize them by A, B, C, D with a subscript X. And similarly, for the incoming Z stabilizer, it's a weight 4 stabilizer. It needs to be mapped to these four bond operators, which we also call them A, B, C, D with a subscript Z. And similarly for outgoing X and outgoing Z, you will have, these bond operators, which we mark them as A bar to D bar. So since every data qubit here participates in 4 incoming X and Z stabilizer and the 4 outgoing X and Z stabilizer, so we have these 8 conditions, right? So if you're just standing on this gadget, you know that you need to produce these 8 operator maps. So with an incoming X, you look around, you find, oh, there's an X stabilizer to my bottom right. So I have to reproduce C and D on these 2 directions, 3 and 4 that I denoted. I marked these 4 directions 1 to 4. And similarly, because there's an X stabilizer incoming on your top left, you have to produce A and B according to the bond operator that we assign on the right. So you have to produce A and B on legs 1 and 2, and etc. So there are 8 operator maps that you need to reproduce through the gadget. So how do we determine, A to D, right? So we determine A to D by looking at, commutation relation between them. So for example, let's focus on, let me annotate. Yeah, let's focus on these two pairs of encoding maps. So this is the first row is an encoding of X, and the second row is encoding of Z. We know that X needs to anti-commute with Z, right? But we know that that their maps overlapped on this leg, right? On the leg in direction 1, right? They overlap on there. So because we know that X anti-commutes with Z, right? So this tells us that AX needs to anti-commute with AZ, right? Whenever they have overlap, right, they need to anti-commute on that overlap, right? And similarly, you can derive all these commutation relations on the right. This will guarantee that your incoming and outgoing poly operators are consistently coded by the gadget. And so we look for a solution of all these equations, and we look for a solution that as simple as possible. So what we find is that A, B, C, D can equal to a same poly operator, and also for a Z. So you only the solution is parameterized by P and Q, which are either X, Y, or Z. And the familiar Hastings-Ha-Fouquet-Tori code actually corresponds to the solution P and Q equal to so the Hastings-Ha-Fouquet-Tori code actually corresponds to the solution with P equal to X and Q equal to Y. So how do we see that? Well, remember your gadget has your gadget has an incoming leg, an outgoing leg, and 4 internal legs. So, and you know that the encoding map right now because you fix A, B, C, and D to be P equals to X and Q equal to Y. So what you can do now is you can reproduce the ZX diagram of this gadget. So that's what we're doing here. So you have an incoming leg, you have outgoing legs, and you have 1, 2, 3, 4, which is the 4 directions over here, 1, 2, 3, 4. And so there's an algorithm that you can use, which is basically the proof of Gottesman-Neal. Which tells you that, Gottesman-Neal says that any Clifford circuit can be simulated in classically, and this is literally the implementation of their algorithm, which you kind of just eliminate different stabilizers in your tableau, and then finally you will just measure you will just measure each individual qubits that are disentangled from this tableau. But in any case, you don't have to care about the detail, but but what you should care is we have this ZX diagram on the right. So in this ZX diagram is the actual ZX diagram of the gadget. And here we introduce another node, this triangle, which is a Y node. So the Y node is an X node conjugated by 3 I phase gate, which this is literally just an S gate. An S gate switches between X and Y. So
just for clarity, you wrote down the stabilizer tableau for using the solution that you found on the previous slide, and then you wrote down that diagram that you have on the left on the next slide.
Actually include the tableau.
Yeah, so this is what you got from the tableau, and then you mapped it to this sort of diagram on the right.
Yeah.
Which looks exactly as the 012 code that we are familiar with.
Yeah.
Okay. And there is a recipe to be able to write these diagrams given a tableau. That's your point.
Yeah. Yeah, so yeah, exactly. So there's a diagrammatic algorithm on ZX calculus that, given a stabilizer tableau of any encoder, you can cook up a ZX diagram. So this is exactly what we're doing here. So so from ZX calculus, the ZX calculus will only bring you so far here. And then you realize, oh, there can be 2 time steps, right, in the intermediate stage. Remember this giant workflow that we're going through. We are currently in the first step, and we want to move towards the second step. And we say, oh, you see, in the second step we need 2 physical qubits. We need 2 physical qubits, and every physical qubit undergoes 2 steps of temporal dynamics, which are marked in blue and red. And when you repeat this gadget, which is in the second row of figures, when you repeat this gadget over time, what you find is that, oh, when you merge this, what we call the dual spatial encoder and spatial encoder, this actually becomes a pairwise measurement in Z basis of these 2 physical qubits, right? So now literally we know what the circuit actually is. So circuit is a periodic. The circuit is a periodic implementation of 3 steps, right? So in the first step, we pairwise measure the 2 Z operators of the 2 physical qubits inside the gadget. And in the first round, marked by 1, we so these X nodes will be connected to other gadgets that are connected to this specific gadget in direction 1. In direction 1, 2, 3, and 4. So in the second round, same thing. You connect these legs to nearby gadgets, which have a Y node. So if 2 Y nodes are connected, it's a YY measurement. If the 2 X nodes are connected, it's an XX measurement. So we kind of materialize this abstract circuit in this way. So we want to draw how the physical qubits are laid out and how the schedule looks like on the lattice, right? So for example, this is an L gadget, by the way. This is the dotted white box in the center. And so and these 2 physical qubits are these 2 vertices on this lattice. And in the round 0, what you have is this pairwise measurement in Z. This is literally the green bond over here. So you know that the first round the green bond is measured. And in the first round, you know, this X node in direction 1 will be connected to a nearby X node. And similarly here, right? So when two X nodes are connected, it's a pairwise measurement in X direction. So literally the blue bonds here are a pairwise measurement of X. And similarly, the red bonds will be connected and they correspond to pairwise measurement in Y. So the spatial layout of the circuit is exactly the Hastings-Ha, you know, Fouquet-Torre code on a square octagon lattice.
So there are two kinds of gadgets. I think in your original slide, you had they were colored white and orange.
Yeah, exactly. So because since the square lattice is bipartite in this case, you have L and R data qubits, and L and R data qubits will become L and R gadgets. Yeah, so you need two gadgets. So they don't. If you step on the R gadget, your encoding map is a little bit different. Actually, you need to rotate yourself by 90 degrees, and that's why, you know, here the R gadgets are obtained from the left gadget by rotating 90 degrees. So
Sorry, can I try to understand the previous slide a little better? So I think what you're saying was that, you know, I have these physical qubits and then I have these ancilla where I do the measurements, where I do the way-to measurements. And there's a circuit diagram here on the left with the in and out. And then I can use ZX rules to condense that into a tensor network, essentially. And then now my space-time dynamical code, the entire circuit can be condensed into this bottom left corner.
Yeah.
And then now you did something very clever, which is something I didn't think of, is, you know, this seems like you were trading, you're saying, let me just trade time for space. Let me convert that into a stabilizer in space on a single time slice, even though those are two connected things on two different time slices. That's derived from the ZX diagram.
Yeah.
And then that just directly recovers the measurement schedule of Hastings-Ha.
Yeah.
I see. And then that whole thing was actually from this square lattice gadget of the surface code.
Yeah, exactly.
Yeah.
Exactly.
Okay.
Yeah, the whole thing is
I
from
see.
here. Yeah, so in the final diagram, like here, the dotted box is literally the box over there, and we figure out that there are two physical qubits inside the box.
Right. I see. Oh, very cool. Thanks.
Yeah, and yeah, I think Charles pointed out a very important point, which is, you know, this dual encoder and these spatial encoders usually need some ancillas, right, to implement. You're literally doing an encoding circuit of some local code, right? But if you merge them on the circuit diagram using ZX calculus, you can merge them into just some local measurements between physical qubits. So yeah, I guess now that this third rule makes more sense, because this internal measurement is literally the pairwise ZZ measurement on this, you know, green link.
Yeah, this is the fusion that you're showing from left to right.
Yeah.
So I sort of want to make one more comment. It sounds like this is extremely general, right? So for general, any quantum LDPC code, I can basically just write this kind of gadget.
Yeah.
And then I can write a diagram and I can do the condensation. I guess what one wants to prove in the end is some sort of distance guarantee at the end. It's not changed. Okay.
Yeah, for LDPC, I think distance, yeah, we have this geometric locality requirement, but I mean, the geometric locality on LDPC code is more tricky, like, so yeah, we should.
Yeah, it sounds like, you know, some sort of flow is sort of localized, right? You have these flows that are closed down into a local region, and as long as that region doesn't contain a logical operator, you're probably good.
Yeah, that's
even for LDPC codes, it just reduces to K locality requirement. As long as K is constant, we still can argue the same thing.
Yeah, exactly. Yeah.
Okay, so maybe I'll just quickly flash over this crazy example that we did, which, you know, I'm not just reproducing any existing Fouquet codes, I'm constructing something new. So so let's so this is actually when I believe this is exactly a year ago when Arpit and I met at KITP. Like, we are literally like next door roommates in the KITP residence, and he came to me like, okay, can we write a Fouquet-Ha code? Like, I remember he was just very casually like showing that, what is a Fouquet code and like what people already done, like what he's envisioning. And yeah, so we eventually made it. And yeah, after a year, yeah. But I'm glad we made it. So just a quick background. So what the Ha code is, it's defined on the 3D qubit lattice. And the stabilizers are all the same on every cube. So it's this 8-body stabilizer. Don't be fooled. This is not that many. There are only 8 non-trivial poly operators. And there are 2 qubits. There are 2 data qubits on the static static Ha code. Which the first poly operator is the poly operator on the first qubit. The second poly operator is the poly operator on the second qubit. And so you can imagine, we do a gadget decomposition, but now the gadget has 2 incoming legs and 2 outgoing legs because there are 2 data qubits per site. And we again utilize, the qubit lattice structure. So we just say, okay, these gadgets are connected just like a cubic lattice, right? It's just connected nearest neighbor. That's it. And so obviously, you have to find a way to parameterize all these bond operators, right? The bond operators can you have essentially 12 different bond operators, which are the 12 edges on this cube. And because, there's a threefold rotation symmetry from 1, 1 to XX, so we can parameterize them in the threefold rotation symmetric way. So that's what we did. We parameterized them in A, B, C, and D. So now you kind of just follow the steps that we did for Tori code, right? So remember, for Tori code, everyone is involved in these 8 encoding maps. So you just write down the encoding maps. But now, in order to keep track of all of these encoding maps, let's write a matrix, right? So the matrix should be understood as this. So in the first 2 columns, are the incoming legs, and the rightmost 2 columns are the outgoing legs. So for example, if I see, there's an II over here, if I see that, let me take a little bit. Yeah, if I see an II over here, right, this corresponds to this row. So the 0, 0 just means, it's II. And this 0, 0 means that there's nothing outgoing, right? I'm talking about the incoming, Ha qubit stabilizer. And if you look around, you'll find that, I have 3 non-trivial legs sticking out, 3 non-trivial bond operators, which is in directions 1, 4, and 6. And there are 8, right? So I write A at 1, which is the first column, and A at 4, A at 6, right? Now you can repeat, for example, let's see this guy. This is XI. So this is 1, 0 in the first 2 columns. And, A goes in direction 3, right? B goes in direction 1, and C goes in direction 6, right? So this is literally the second row, right? So you have 8 qubits, not 8 qubits. You have 8 sites on the cube. So you have 8 encoding maps until here, right? And you have another 8 because you have 8 outgoing stabilizers, which has this site is involved, right? So you have in total 16 rows, and similarly for Z, right? So now you just need to solve the consistency condition, which is this. So you just solve that HX times HZ is 0 mod 2, right? This is what people always do when talking about encodings. And you solve HX HZ equals to 0 mod 2, you find that the solutions correspond to these bond operators. And 0, 0, and 1, 1 just means that there is a non-trivial 0 means there's no poly, and 1 means there's a poly X or Z based on the foot script X or Z. So again, you do this construction of ZX diagram, like of the encoder based on the solution, and what you find is on the right. So since now every bond operator is weight 2, there are actually 2 times 6 equal to 12 internal legs, and 2 incoming, 2 outgoing, and 12 internal legs, which goes directions from 1 to 6. So the first poly operator is the first leg, which is the unprimed leg, and the second is a primed leg. Yeah, but we figure out that this guy actually has a very neat ZX diagram, which is over here. And if you repeat this over time, you find it's actually very, very clean. So you have a 5-round schedule, like on the bottom right. So yeah, the point that if you merge this dual encoder with the encoder, if you merge this dual encoder with the encoder, what you find is that this is essentially so this part is merged into this part. So so this is basically a measurement circuit that pairwise measure, z times z on these 3 qubits and z times z on that 3 qubits. Yeah, and that's basically it. So we have a 5-round schedule from the gadget perspective. Now we just need to lay them down on the cubic lattice. And yeah, I'm just gonna flash, how it looks on the lattice. So it looks like this. So remember, every gadget is now replaced by every gadget is now replaced by 6 physical qubits, right? Because as we said, as we found out on the ZX diagram, since we have that layout, over here. We have 6 qubits going over time, so we need 6 physical qubits per site instead of 2 data qubits. And these physical qubits undergoes the 5-round schedules given by the ZX diagram, in which in round 0 you measure the z times z for these 3 guys, which is this time step, and 1, 2, 3, 4 is given by the ZX diagram. But in any case, it looks like this. It looks kind of crazy, but I mean, we checked that it worked. Yeah.
So 5-round schedule is when you have these 3 body measurements.
Oh yeah, very good point. Yeah. So in the round 0, 1, 2, 3, yeah, in round 3, you have this 3 body measurement. Yeah, remember that this corresponds to a 3 body measurement, z z z.
And round 0,
it's a
you
2 body measurement.
You have those 3 nodes connected together.
Yeah.
So since they overlap, would you need some like, can you do them together in one step?
I don't know. It's kind of engineering issue, right? Like, if you have hardwares that supports, native pairwise measurement, then maybe it's parallelizable. But if you're just talking about, very rigid kind of hardwares, then you might need to do them in 2 steps, right? Because you cannot parallelize 2 CNOTs.
Yeah, that's all.
Yeah. Yeah, but so yeah, we're just giving it like one number as a step, but inside the step there could be sub steps depending on the hardware. Yeah. Okay. All right. So finally, I think I'm running out of time a little bit, so maybe I'll just wrap up. So our work has other details inside the paper, which includes gadget. So since we have this notion of gadget decomposition as a tool, it doesn't really doesn't only constructs it doesn't really only construct dynamical code. It also enables discussion of dynamical codes themselves. So for example, from the gadget decomposition, we can understand what are the local equivalence class of dynamical codes, which means that maybe some dynamical codes look very different, but they're actually the same from the ZX diagram perspective, or from the spacetime circuit perspective. And we can also understand fault tolerance of dynamical codes from gadget decomposition, as I think Charles and Arpit would mention, like the code distance argument. And the third is we can actually incorporate fabrication defects in hardware, since we have this flexible structure of gadgets. Like some fabrication defects just corresponds to take out some gadgets or take out some connectors that just simply are defectful and you cannot use them as part of our circuit. So we find that our construction using gadget decomposition is also very, very flexible and very powerful in incorporating all of these fabrication defects. And yeah, in the future, this protocol can be implemented on good LVPC codes. And we also trying to, explore, other interesting direction. For example, maybe it can realize, non-Clifford dynamical codes, maybe non-Clifford logical gates. And we can also look at, whether there are, new kind of faster, decoding strategy that are enabled by this gadget decomposition. Yeah, so with that, I'd like to, thanks for your attention.
Awesome. Yeah, thanks, Yichen, for a very nice talk. And if there are any questions, I think, we have a few participants here. So if there are any questions,